Hello guys, welcome to today's lesson in which we're going to talk about the topic 1.3 radicals, radicales. And we're going to look at these three things, which are simplification of radicals, and then addition and subtraction of radicals, and finally something called the rationalization of the denominator. So we're going to see these three things in that order. So let's first talk about what this symbol means. When I write something like this, guys, when I write this symbol, I'm going to tell you how to read it first. This is read as the nth root of x. I repeat, the nth root of x. In Spanish, this is read as la raíz enésima de x. La raíz enésima de x. Okay, so what does this symbol mean? What does this mean? This symbol. I know it's a little weird, okay, and it's not very hard. It's not very simple to understand, such as a fraction or an integer or a decimal. Okay, I understand that these numbers are somewhat difficult to understand for a young mind. But why is that? Let me tell you why that is. First, again, what does this symbol mean? It means the following: the nth root of x is a number. We're gonna define it in this way with the property that when you multiply such number, all of this, when you multiply it by itself n times, like I'm multiplying the same number, the nth root of x, by itself n times. So you by now you know that the three dots mean and so on until a final factor. Okay, when we multiply this number by itself n times, there are n factors here. Then what we get as the result is the number inside the radical. Okay, x. That is the definition of this number, guys. That is what this number means. It's a number with the property that when you multiply it by itself n times, that is as many times as the index of the root tells you, what you get is the number inside the radical, x. Okay, let's put into work this definition with some examples. For example, following that definition, if I write something like this, the square root of 3 times the square root of 3, this is by definition 3. Okay? Why? Because I'm multiplying this number by itself 2 times, okay, as many times as the index is telling me, and I'm gonna get the same number inside the radical. Another example. Let's consider the cubic root of 4 or the third root of 4. What is this number? What is this number? This is the number with the property that if you multiply it by itself 3 times in this case, because that's the index is 3, you see? If you multiply by itself 3 times, you get the name inside the radical, which is 4. What about the fourth root of 5? Let's put another number. The fourth root of 7. What is this number? What is this number? It's the number such that when you multiply it by itself as many times as the index tells you, which in this case is 4, you're gonna get the number inside the radical. So please try to get used to the idea that these numbers, even though you don't know what the decimal representation of these numbers are, okay, it's somewhat difficult to know the decimal representation of these numbers. They are simple, valid, normal numbers, okay? Just like the number 3, just like the number 1/2, etc. What is this number? What you have to answer is this. Is a number such that when I multiply it by itself 4 times, I get 7. That's what this number is. And that is enough to know, okay? Do you need to know what number exactly that is? For example, do you need to know whether this number is 0.8976? No, no, no. You don't need to know the decimal representation, okay? It's a good thing to know, but you don't need to. This number can be written as it is on its own, and you don't have to calculate its decimal representation to say that you know this number. Just by writing this number, you're telling me or you're reading that you know this number. I hope you understand that idea. Okay, so that I believe that's the only definition that we need in order to proceed to the simplification of radicals. Let's go there. Simplification of radicals. This is the first thing we're gonna do today. And I'm gonna show you 4 examples. You're gonna pay attention to how they are solved, and you're gonna do the rest on the workbook. So for example, let's simplify the number, the square root of 8. And by the way, remember, when I don't write the index in here, that means that there is a number 2. That is the only case in which you can ignore the index, okay? When it's 2. So this is read as the square root of 8. And they want me to simplify this. What does that mean in the first place? Okay, what that means is to somehow reduce the complexity of this number and re-express it in a, well, in a simpler way, right? That's what simplification means. You're going to understand what that means in a moment. So how do we do this? The first thing you have to do, guys, is look at the radicand, which is 8 in this case, and I want you to factorize it in prime factors, okay? The factorization of 8 in prime factors is 2 times 2 times 2. 2 times 2, 4 times 2, 8. Are all of these numbers prime numbers? Yes. Therefore, this is the prime factorization. This is what we know as the prime factorization of the number 8. I'm gonna show you another factorization which is not prime. What if I say 8 equals 4 times 2? This is perfectly right. And this is indeed a factorization of the number 8. But this is not a prime factorization. Why not? Because this number is not prime. And therefore this doesn't classify as a prime factorization of 8. Okay, now if you don't remember how to perform prime factorization, let me remind you very quickly. What you do is this. I suppose you know this little method about the table. You're gonna write the number 8 and this sort of table, and then you're gonna begin by trying to divide this number over integers starting from the number 2 as many times as possible. Look, I'm gonna try to divide 8 by 2. Can I do that? Yes. What do I get? 4, because 8 over 2 is 4. Now look at this number now, number 4. Can I divide this number over 2 again? Yes. What do I get? I get 2, because 4 over 2 is 2. We have now the number 2. Can I divide this over 2? Yes. So we write it down. We divide 2 over 2, we get 1. And once you get to 1, you are done with the process. And all of this list of numbers, 2, 2, and 2, when you multiply them together, this gives you the prime factorization of the number that you were trying to factorize in primes. So that's how it works. Okay, so now we know that the prime factorization of 8 is 2 times 2 times 2. Perfect. So what do we do next? What we do is re-express this number as the square root of its prime factorization. 2 times 2 times 2. Okay, they are the same. And then you're going to separate the root of a product of numbers. Okay, when you have a product of numbers, 2 times 2 times 2, you can separate the root, and this is going to be equal to the square root of each of those factors, like so. Okay, you can always do this. Perfect. And now what can I do now? Okay, now you're going to use the fact that since you're working with the square root of 2, and remember that by definition the square root of a number x, this number is the number with the property such that when you multiply it by itself 2 times, what's going to happen? You're going to get x, the number inside the radical. Okay, this number has this property, so let's use that property in here. We have the square root of 2 times the square root of 2. By definition, when I multiply the square root of a number by itself again, what I get is the number inside the radical, so I get the number 2. So basically this is equal to the number 2, and this one remains in there, and I have to just place it right there, multiplying the number 2. So basically this is 2 times the square root of 2, and that is the ultimate simplification of the square root of 8. We say that the square root of 8 is equal to 2 times the square root of 2, and you can make sure by calculating that thing in the calculator. If you calculate the square root of 8, and if you calculate 2 times the square root of 2, you're going to get the same numbers. Next example. Example number 2. What about the square root of 32? I'm going to use the index now. I could ignore it, but I'm going to use it. Okay, let's simplify this number. What do we do first? We factorize the number 32 in primes. And when you do that, I'm not going to do it for you. You're going to do it on your own. You're going to get that this is 2 times 2 times 2 times 2 times 2. 5 times the number 2. So I'm going to replace this as the cubic root, the square root of 2 times 2 times 2 times 2 times 2. Now, I divide the radical into each of these factors. The square root of 2 times 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 the square root of 2. Fine. And then I make use of my property. If I know that the square root of a number x is the number with the property such that if I multiply it by itself 2 times, I get x, then I can do the same in here. When I multiply these 2, I'm going to get 2. When I multiply these 2, I'm going to get 2. And this one remains alone or without any simplification. And what I get in the end is the number 2 times 2 times the square root of 2. So 2 times 2 is 4 times the square root of 2. And this is the final simplification. So you see, we're just converting or using this factorize in order to represent all of this multiplication as just the number 2, and the same for this one, you see. So that's how we are simplifying. Example number 3. What about the cubic root of 16? Now we're dealing with a cubic root. Okay, so first step, I'm gonna represent the number 16 in prime factors as the product of prime factors. When you do that on your own, you're gonna get 2 times 2 times 2 times 2. This is the prime factorization. So I replace this number as the cubic root of 2 times 2 times 2 times 2. That is the first step. Next, I divide the radical into each of the factors. So this will be equal to the cubic root of 2 times the cubic root of 2 times the cubic root of 2 times the cubic root of 2. So far so good. Now, how can I simplify this? Well, we know the following. By definition, the cubic root of a number x is a number that has the property that when you multiply it by itself 3 times, as many times as the index tells you, 3 times by itself, what do you get? You get the number inside the radical. You see? And I can use this fact, which is my very most basic fact. Okay, you need to understand this first and foremost, which is the very first thing I told you in this lesson. And I can use it for my convenience in here because I want you to look at this. We have the cubic root of a number multiplied by itself 3 times. You see? And basically, when I multiply this times this times this, I'm going to get 2. I'm just using this very fact. Perfect. And this number remains alone without any change, so I just write it down. So basically, what we have concluded is that this is my final factorization, by the way. My final conclusion is that the cubic root of 16 is equal to 2 times the cubic root of 2. And this is my result. Let's go to a final example. Example number 4. The square root of 15. Let's represent 15 as its prime factorization. When you do it, you're going to get 3 times 5. Let me do this one. Okay, you have 15. You do the table. Can we divide over 2? No. Can we divide over 3? Yes. 15 over 3, 5. Can we divide over 2? No. Over 3? No. Over 4? No. Over 5? Yes. 5 over 5, 1. I get 1. I'm done. The multiplication of these numbers is my prime factorization. Okay, so I'm going to represent the square root of 15 as the square root of 3 times 5. I separate the root. I get this. And now if you notice, there doesn't seem anything to do. There doesn't seem anything to do in this case. Okay, we cannot do anything. Why? Because we don't have the square root of a number multiplying by itself 2 times. We have the square root of 3 times the square root of 5. But we cannot apply the property that we know in here. Okay, if we had, for example, if we had this, then I could simplify these 2 into 3. But I only have one of them, one square root of 3 and one square root of 5. So what can I do? I cannot do anything. So what would be the answer in this case? Can the square root of 15 be simplified? No. No simplification. Okay, this number cannot be simplified. Okay, that would be an answer. Okay, so that's how simplification of radicals works. Now let's go to addition and subtraction of radicals. Okay, remember, when we have something like this, x plus 2x minus 5x, what do? We just simply add the coefficients, which is 1, 2, and minus 5, and we are done, right? 1 plus 2, that's 3, minus 5, that's minus 2, and we add the x. So this will be my answer, right? X plus 2x minus 5x will be minus 2x in the end. Okay, we're gonna use this the very technique or process in order to add or subtract radicals. We're gonna use the same thing, the same idea. So first example, example number 1, 2 times the square root of 2 plus 4 times the square root of 2 minus the square root of 2. Okay, so all I need to know is this: do we have, pay attention to the root, do we have the same index in all the roots and the same radicand? If the answer is yes, then we can simplify like I just did the x's over here a moment ago. Okay, I'm just gonna have to add or subtract the coefficients. So my coefficient here is 2, my coefficient here is 4, and my coefficient here is -1. So I just add them. 2 plus 4 is 6, -1 5 times the square root of 2, and this will be the solution. Number 2, the cubic root of 5 plus 4 times the cubic root of 5 minus 2 times the cubic root of 5. So first thing, if you want to add or subtract this expression, make sure to have all the indexes and the radicands the same. Are the indexes the same? Yes. Are the radicands the same? Yes. Okay, so we can proceed. What is my coefficient in here? It's number 1, right? It's over here, but it's not written, as you know. What is my coefficient here? 4. And what is my coefficient here? -2. So let's just add 1 plus 4, 5, -2, 3. 3 what? 3 times the cubic root of 5. And that will be my solution to all of these operations. Number 3, let's consider the square root of 8 minus the square root of 2 plus the square root of 12. Okay, same question. Are the indexes and the radicands the same? All the indexes are the same. They are 2, right? But the radicands don't seem to be the same. I mean, they are not the same. That's for a fact. Okay, but that doesn't mean that you cannot do something, at least in this case. You know, in some cases you won't be able to do anything. But in this case, you can. Why? Because in order to do this type of operations, addition and subtraction of radicals, the first thing you have to attempt is to simplify each of these radicals. Okay, if they can be simplified, you have to simplify. Okay, I'm gonna do the simplification for you right now, and then you're gonna have to be able to get to the simplifications on your own. The square root of 8, after you simplify, you will get 2 times the square root of 2. In the meantime, just believe me, okay? You in a moment you will get from here to here on your own. The square root of 2 cannot be simplified. That is already simplified in the most possible way. And the square root of 12 can be simplified as 3 times, no, I'm sorry, 2 times the square root of 3. This is a simplification of the square root of 12. Okay, now what? After you have simplified all of your original radicals, what you do is you try to add and subtract like we did in these two examples, okay? Look at these two numbers. Do they share the index? Yes, it's the number 2 in both of them. Do they share the radicals? The radicands, I'm sorry. Yes. because the radicands are the number 2. So I can add, or in this case, subtract these two numbers. What's going to be the subtraction? Look at the coefficients. 2 minus 1. Add them or subtract them. 2 minus 1 is 1. And 1 times what? The square root of 2. Which can be written simply as the square root of 2. And what about the other number, this one? Well, this we cannot do anything with this, okay? We cannot do any change. So basically, all of this, in the end, will be written like so. This is the simplification of this, all of these three operations. Number 4, the square root of 3 plus the square root of 5. Same question, are the indices the same? Yes, they're the number 2. Are the radicands the same? No. One is 3 and one is 5. Try to simplify. When that happens, try to simplify. Now the problem here is that these numbers cannot be simplified, okay? I want you to think about why the square root of 3 and the square root of 5 cannot be simplified. Okay, so this cannot be simplified any further. So what's the answer here? It's gonna stay the same. There is nothing to do here, okay? You cannot put these two numbers together like in the same way we did in the first example or the second example, or like we did with these two numbers becoming the square root of 2. No, we cannot do that in here in this case. Number 5, the square root of 3 plus the cubic root of 3. Same thing, ask yourselves the question, are the indexes the same? In this case, they're not. Okay, so in here there is nothing to be done because the indexes are not the same, and the answer is going to stay the same. There is no way you can simplify this any further. So it's going to stay like that. So this is how you simplify, guys. What you do is you try to simplify first all your radicals, and after you do that, you make sure to add just like normal variables. And the final thing to do today is the rationalization of the denominator. What's that mean? Okay, first example. We have 2 over the square root of 2. We have a fraction right here. And this technique, known as the rationalization of the denominator, what it means or what it asks from you is to rewrite this fraction as another fraction. I'm gonna just write this for the moment. I need to rewrite this as another fraction which, pay attention, does not have any root in the denominator. That's what we want. Because if you look at this fraction, there is nothing wrong with this fraction. It's a perfectly good fraction, but it has a root in the denominator. And for certain specific tasks or techniques in upper semesters, we may want to rewrite this fraction as an equivalent fraction which does not have any root in the denominator, okay? So that's what we want. That is the problem, basically. How can I get an equivalent fraction to this, but with the property that it doesn't have any root in the denominator? Okay, what we do is very simple, and it's the following. You're gonna multiply the fraction's numerator and the fraction's denominator both by the same number, and in this case the root. Okay, I'm gonna multiply this. I'm gonna do it in blue. I'm gonna multiply the 2 times the square root of 2 and the square root of 2 times the square root of 2. Now I ask you, is doing this valid? Like, can I multiply a fraction's numerator and a fraction's denominator by the same number without altering the fraction itself? Yes, we can. It's like when you do this. If you have 1/2 and you go, okay, I'm going to multiply 1 times 2 to get 2, and 2 times 2 to get 4. If you notice, this new fraction that came up, 2/4, is the same as your original fraction. So as long as you multiply numerator and denominator by the same number, you're good to go. Okay? Okay. So why did I want, let's go back to the example, right? Why did I want to multiply both numerator and denominator by the square root of 2, which is the denominator? Because if I do that, observe what's going to happen. What am I going to get in the numerator? I'm just going to get 2 times the square root of 2. Nothing else to do there. But what is the square root of 2 times the square root of 2? By now, you're maybe already familiar with this. That's going to be equal to 2. You see? And we have obtained a new fraction which is equivalent to my original one with the property that it doesn't have a root in the denominator. You see? Now, if you can simplify a little, go ahead. For example, in this case, we got 2 times the square root of 2 over 2. Well, I can cancel this number and this number, and in the end, I just get the square root of 2, you see? So you can do that as much, every time it's possible, do that please. So this is the result. The result is the square root of 2. Example number 2. What about 3 over the square root of 3? Now let's write 4. Let's write 4 here. Like so. Okay, same idea. We have a fraction with a root in the denominator. And we want to find an equivalent fraction that doesn't have a root in the denominator. What do? I multiply numerator and denominator by the same root, which is the denominator itself. So I'm going to multiply 4 times the square root of 3 and the square root of 3 times the square root of 3. And let's see what happens. 4 times this number is going to stay like that. There's nothing else to do. Over the square root of 3 times the square root of 3 is by definition 3. And we are done. There's nothing else to be done here. We cannot simplify any further. We cannot divide 4 over 3, etc. So it just stays like so. Number 3, 5 over the cubic root of 2. Now we have a cubic root. Let's see what happens here. Same idea. I need to multiply numerator and denominator by the same number, which is the denominator itself. But in this case, I need to multiply 2 times by the same number, you see? I'm multiplying the numerator by the cubic root of 2 times the cubic root of 2. So I'm using the cubic root of 2 times, and the same below. The cubic root of 2 times the cubic root of 2 times the cubic root of 2. Now, why did I use another one here? Because if you noticed in the other examples, I just used one factor for the numerator, one factor for the denominator. But here I'm using it twice. Why do you think that is? What could be the possible reason? The possible reason, guys, is so that I can employ the property of the cubic root. The cubic root of a number is a number that when you multiply by itself 3 times, you get the number inside the radical. Okay? So you have to have at least 3. You see what I mean? 3 cubic roots. And that's why I multiplied this cubic root times itself one more time. I needed 2. With just one, if I'm gonna erase it for a moment, with just one of them, like so, this is perfectly okay. But I'm not gonna be able to use this trick or this property in order to reduce in order to get rid of the roots in the denominator. So I need another one, another of those, so I can complete a 3 of them, and I can employ this fact. So this is going to be equal to 5 times the cubic root of 2 times the cubic root of 2 over 2. And this would be your answer. You see? So that's how you rationalize the denominator. Basically, you're trying to get rid of the root in the denominator. How? By multiplying numerator and denominator by the same number, in this case, the root that you're trying to get rid of. You see what I mean? Okay, so that completes the lesson, guys. Go to the exercises, try to do them all, and if you have questions, I can answer on Monday. So thank you very much, and have a great weekend.